Hi again. In this movie, we will continue our review with the Hagen-Poiseuille flow. If you remember, it's exactly what we did before, just instead of a rectangular channel, we have a cylindrical channel, and we don't anymore have any wall motion. We only have a purely pressure-driven flow. Pressure is larger at the inlet, and pressure is lower at the outlet of this cylindrical pipe. And what we noticed is, if you look at your notes, after solving the Navier-Stokes equation and also satisfying continuity, we got this velocity profile given the assumption that velocity as a vector has no components in the radial direction, has no components in the theta direction, and it's only Vz that is non-zero, which can be a function of r. To remind you again, the coordinate system usually for these cylindrical problems has this kind of geometry that r, z, and theta are shown here. And this assumption that velocity has only non-zero components for Vz is something that can actually be invalid in certain problems. Indeed, if you go to really large Reynolds number turbulent-like flows, we saw that this can be not anymore the case. And we have different components of velocity in the theta and r direction that become significant, and we need to deal with them. But for now, in the limit of laminar flows, fully developed laminar flows, and in a moment we explain what we mean by laminar versus turbulent, we assume that this kind of velocity profile is our solution. We plug that inside Navier-Stokes equation with this hypothesis that we made, and we got this velocity profile that has this kind of mathematical form. And it gives us a parabolic profile. It has zero velocity, as it should give us at the position of r equal to r, which is the edge of the cylindrical geometry or domain that we are solving the problem, and that's due to the no-slip boundary condition. And the maximum velocity happens at the center of the pipe, which is r equal to 0. Now, one way to think about this problem and having this velocity profile is to think about the overall volumetric flow rate that we have in each cross-section of the pipe. If you calculate that overall volumetric flow rate, you can divide that over the cross-sectional area, which is pi multiplied to r squared. The resulting velocity is what we call average or mean velocity. In some ways, it's representative of how much on average fluid element we are carrying through this cross-section. How many fluid elements per unit time on average, or what's the average velocity that fluid elements are passing a cross-section in this type of flow. For any velocity profile, you can calculate this mean velocity. And what we noticed is once you do the calculation for the mean velocity based on this solution, you will notice that things such as pressure gradient and other parameters can be rearranged in an interesting manner. Let's do that together. Just as a reminder, you can look at your notes again. We defined a combination of some of these parameters. We defined them as a parameter called friction factor F, which is defined as the pressure drop that you have, delta P, which here will be P plus minus P negative, divided by half of rho average velocity or mean velocity squared inside parentheses, and then another geometrical factor, which is the aspect ratio of the pipe, L over D, where if you are curious to know that D is the diameter, which is nothing other than 2 times radius of the pipe. And at the same time, we also use another dimensionless number, which is Reynolds based on diameter. And that Reynolds is rho times the mean velocity V, or with a bar on the top, times diameter D divided by mu. With the definition of these two parameters, which in a moment we explain why we really define and use these two parameters, we could actually use the solution of the velocity profile, calculate the average velocity, and connect these two parameters, friction factor and Reynolds number, to each other. You can already see that they should kind of get combined together, because in this solution we have indeed the pressure gradient, which is nothing other than delta P over L. This term is delta P over L appearing here. And at the same time, when we integrate it and calculate the volumetric flow rate, you can easily see that something like average velocity will show up there, and these two relationships get combined. That is something I really encourage you to go and do the algebra and check the algebra with what has been covered in the lectures. But once you do that, you will notice that you get an interesting relationship between friction factor and the Reynolds number, and you can actually plot it on a log-log curve. So log of the friction factor on the y-axis, log of the Reynolds number on the x-axis. And we got a linear relationship on the log-log that goes like this. Experimental data Garrett has shown in his lecture videos that agree very well with this curve, which is linear on log-log. And around a certain Reynolds number of approximately 2000, we start to get some deviations to some other possible solutions, which usually show relatively flat curves at large Reynolds numbers. We discussed that this large Reynolds number limit is what we call turbulent flow in the pipe, and the low Reynolds number is what we call laminar flow. The deviation of the results from the solution that we had for the laminar section is mainly due to the fact that the velocity profile not anymore satisfies this initial assumption that we made. You have indeed components of velocity in the r and theta direction that are significant, and we need to take them into account. However, this line, just based on the laminar solution that we have, can be precisely described as F being equal to 64 divided by Reynolds based on diameter with sub d. This is an important relationship to keep in mind, and we come back to this relationship in a moment. But what I want to draw your attention to is the idea that, again, solving Navier-Stokes equation enabled us to find the velocity profile. Having the velocity profile, we could find the relationship between things like pressure gradient and the average mean velocity in the pipe. And this is an important relationship that can help you design pipe networks, because now you have two dimensionless groups that are connected to each other. But for example, if you know what is the average mean velocity that you need in a pipe, if you use this relationship at a certain given Reynolds number for a given liquid like water with a certain viscosity and density, you can actually calculate what would be the friction factor for the problem of interest, and that friction factor would give you back the pressure drop needed. So then when you go and design a pipe system and want to buy a new pump, you make sure that that new pump can actually guarantee this match of pressure drop for the desirable average velocity or average flow rate that you are planning to have in your pipe network. And you all have seen examples of this in your undergraduate courses, so you can actually do a fast recap of some of those examples if you have time. But the idea of defining dimensionless groups such as friction factor and Reynolds has a slightly deeper roots. And in the next video, as we move towards the review of dimensional analysis part, we talk about where exactly these two numbers come from and how you can wrap your head around their nature, their origins, and their possible applications in different problems.